Hello everyone. In this video we'll learn how to construct a feed-forward neural network using numpy. Before moving ahead, the result of the sum product plus the bias will be indicated using small z or capital Z depending whether it is for one sample or the entire data set, and the result of activation function will be shown using small a or capital A. So let's write the code for one hidden layer neural network with two neurons. If you have not watched my previous video, which was on basics of neural network, please watch it. In that video, I have explained the entire matrix calculations for this network. So I'll be writing the code based on those calculations. Even if you have not watched the video, it's fine because we'll continuously refer to those calculations to write the code. Okay, so the only thing you should worry about is keeping dimensions of the matrix consistent as your input moves towards the output. So we have to suppose now we want to create a data set, and we want the data set to have certain rows and columns. So suppose we want m observations and we want n columns. It is better to define it this way so that we can later change the numbers. Suppose we want 100 rows and we had 3 features. So let's check how the X matrix looks like. Oh yeah, we have to run the numpy first. So yes, this is how our X matrix should be. We should check the shape always. Yes, 100 observations and we have 3 features. Now we have the X matrix. Now we need the weights, and we know that each input will be passed to all the neurons. So if we refer to our calculations, we can see that the weight matrix is supposed to be in the shape of 3 by 2 when 3 was the number of features and 2 was the number of neurons. So we'll create the first hidden layer in this one refers to the first layer. So the first layer we wanted 3 features and 3 was the number here n and 2 neurons, so we'll keep it as n neurons. Again, these are for the first layer, so we'll keep it that way. Now let's check the shape of the weight matrix. Yes, it is correct. There are 3 rows and 2 columns. These 3 weights are the weights of the first neuron, and these 3 weights are the weights of the second neuron. So now we have the data and now we have the weights. We can easily calculate the output of g of x, which is z. So okay, we have already checked the dimensions. Let's see how the product of the matrix X along with the weights looks like. X at, this is what we wanted. When you multiply matrix of m observations and 3 columns with 3 by 2, you get m by 2. So this matrix is what we have it here. X multiplied by weight matrix 1. 100 by 2. So now we also have to add bias to it, and we have not created bias. So first let's create bias. And the bias is of shape. The bias matrix is of shape m observations and it has two columns. So it's not necessary to create of, okay, let's see, let me show you. M observations and it has two columns because of two neurons. Yeah, 100 by 2. And okay, so now we have everything we need to get the output of g of x. So x multiplied by the weight matrix gives you 100 by 2. Now you have to add bias 1 to it, and this is what you will get. Now we are at this stage, we have the output of g of x. Now we have to apply activation function on it, and since it is a hidden layer, we know that we can use ReLU or leaky ReLU on it. So let's see how ReLU works. This is the weight matrix, this is x multiplied by weight matrix plus bias. Okay, and what is ReLU doing? ReLU will just select the maximum value between 0 and this value. So we can just do it using one line of code. This, so this is the output of the activation function of the two neurons. The first column is the output of the first neuron, and the second column indicates the output of the second neuron. Now again we know that they are further inputs to the output neuron, and again since there are two inputs, this neuron will have two weights attached to it. So again, let's code for that. We'll show this using a1 or capital A because it's for the whole matrix. So this a1 is the output of the activation function for the first layer. And similarly, if we wanted just the sum product, we could have shown using z1 is equal to okay. Now we have to feed the output of this layer into this neuron. And how do we do that? Based on our calculations. So if you remember, we are at this stage, we have the ReLU output, and again the final neuron is of the shape 2 comma 1. And why is it 2 comma 1? Because it has two inputs and it's just one neuron. So again we'll use that to code for the output neuron. Here the shape was 2 comma 1, where 2 was the number of inputs. So which is the number of inputs for that is a1 dot shape. So this, we are using this because this is the input and we want to keep it general, as I told you before. And 1 because we just have one neuron in the second layer. Let's see how the weight matrix for the second layer looks like. N neurons 2 is not defined. Okay. Okay, actually we just had one neuron. Yes, this is the weight matrix for the second, like the final output neuron. Now again, what we just have to do the same thing. We have to get the product of a1 at weight matrix 2, which is consistent with our output. Again, this will, we have to add bias to it, and we have not defined bias. So let's define bias here. And bias is just one, because it's just one, or you can say this is the final answer. This final answer is of the shape 100 by 1. Why 100 by 1? Because in the calculations we had learned about this is why 100 by 1. That means for each observation there was a y value which was the hard egg, which was binary. So it was 0 comma 1. We were discussing the prediction of heart rate based on certain factors. So this, the dimension matches with this, which is 100 by 1. So this is how you vectorize the neural network calculation. Now we'll see how to write functions and how to create a class for it. Okay, let's create a class for neural network. So we will create two classes. One class is for hidden layer and another class is for the output layer, because hidden layers have the same function. So the class hidden layer, the first, okay, all the layers have two tasks to perform. They have to take the input and produce the sum product of the inputs and the weights. The bias has to be added, and then that subproduct will have to be passed to the activation function to get the final output. So this is the task of all the layers, but there will be a difference in the activation function in the output layer and the hidden layers. So that's why I am creating two separate layers. So the first thing is we need to calculate z, which is the sum product. And to calculate the sum product, suppose this is the hidden layer, to calculate the sum product we need inputs and the weight matrix. So let's first define the weight matrix. And to define the weight matrix we need number of neurons and number of features of the input data. And the weight matrix has the shape of, if you remember, this is the shape of the data where there are 3 features and m observations, and this is the weight matrix. So there we had 3 rows because there were 3 features, and 2 columns because we had 2 neurons. So the number of columns were dependent on number of neurons, and the number of rows were equal to number of features. And we were calculating the sum product of the input data at this is how you calculate the self input data multiplied by self dot weight matrix. But we have not yet defined the weight matrix, so let's define it. The weight matrix takes number of features as the rows and number of neurons as the column. So once you have this weight matrix, yes, if you remember, we also need bias for the final answer. So self dot bias is equal to np dot random dot rand n. So here I am using the number of rows as 1 because it doesn't matter, because in numpy even if you define a shape like this and when you add it to a matrix, this will get broadcasted and it will become equal to the shape of this matrix. So that's why even if I write here number of rows as 1 and the number of columns as 2, it will automatically get broadcasted when you try to add this. So now to calculate the z, we have input data multiplied by self matrix, and we need to add self dot bias. And the next function we want it is calculate a, which is when you pass it through the activation function, and we are using ReLU activation function. So this is what ReLU does. ReLU will select the maximum of the two value. Either it will be 0 or it will be the maximum of this value. So this is, let's see if our hidden layer works. So suppose we create neural network, first layer is equal to, and we have suppose 3 neurons. Suppose instead of 2, since we have created general code, let's see first. Okay, let's say suppose we have 2 neurons and the number of features are 3. Yeah, so it works. Similarly, we will have nn dot bias also. Okay, this works. So now let's calculate. We already have the input data defined, so let's calculate z. To calculate z, we need only, to calculate z, I think we have defined it wrongly. To calculate z, we only need the input data and self, because the weights and bias are already defined. Let's see if we got the answer, nn dot z, and let's check the shape. Yes, it is correct. And once we have z, we need to calculate a, and to calculate a, we only need self, because it will anyways take the maximum. So you don't need to define self. So and we have the answer. Again, we'll check the shape. So yes, so that means our hidden layer works perfectly. So let's now define the output layer. Again, the output layer has one neuron. So to initialize the matrix, weight matrix, we need, so actually this will always be 1. So that means we only need the number of features, because in the output we'll always have only one neuron. And for the output, if you look, the output neuron has to have a shape of, this is 2 comma 1 because we have 2 inputs, and 1 column because there's only one neuron. So the number of features input as the number of n features will be the column number of rows in the weight matrix, and there is one column because there is one neuron. Again, there will be a bias, and the bias again will only be 1 because we have only one neuron. Again, we wanted to do two tasks. One is to calculate z and one is to calculate a. To calculate z, it just needs the input data. And what is the input data? Input data we'll provide. So I think we can simply copy the calculations from here, not the calculate a part, because here the ReLU function, here the activation function will be different. So in the output layer, if suppose we are dealing with a binary classification problem, then we'll use sigmoid function as the activation function in the output layer. So self dot a is equal to 1 divided by, I hope you all know the sigmoid function. It is 1 divided by 1 plus e to the power minus z, and this is the z. So we know this hidden layer works, so we just need to check the output layer. So we have nn.a. Now let's check the output layer, and that will be the neural network second layer. And the number of features, now we have 2 as the number of features which will be used as input. You can see from the diagram we have 2 inputs. So 2 nn2 actually, and this should have been nn1 the whole time. Let's check again if the code works. Yes, it works. Yes, we have this. Again we have the bias. Now let's calculate z, and the input data is neural network first layer dot a. And we have the z, and similarly just check the shape once, calculate a, and again to calculate a, what do we need? We don't need anything. This is a. So in the case of binary prediction, what we have achieved, what we have got is the probabilities, predicted probabilities. Now if we want to just convert this into 1 or 0 using the condition that if it is more than 0.5 or if it is less than 0.5, what you can do is, this is the answer. It will automatically do it for all the observations, and if you want to convert this into an integer, you can just write this code, and here you will get as if it is 0.5, it is more than 0.5. If all of the observations were more than 0.5, then it would have converted everything into 1, and this is the final answer. Now you can compare this with the original observations, and then you can calculate the final loss or the final accuracy of the model. So this is how you construct a neural network class. This method will get more complicated as we get into backpropagation. We'll study backpropagation soon. I hope you enjoyed the video.